Hi everybody, today's lecture 24 and today I get to tell you about something that's pretty amazing, very amazing, the divergence theorem. Here, a small clarification or even correction from last time. So last time I told you that the divergence theorem was due to Gauss, and in fact, indeed it was discovered by Gauss in, let me check my phone, 1813, but it happens, it was already known to Lagrange 15 years earlier, 15 years before. So according to Wikipedia, the theorem was discovered by Lagrange in 1762. Then 50 years later, it was rediscovered by Gauss, and at the same time, Ostrogradsky, who's a Russian mathematician, and who actually did a little better than Gauss. Not only did he discover that the theorem was true, but he also gave a proof of the theorem. Later on, the theorem was again rediscovered by Green, by Poisson, and by Sarrus. Okay, but with the historical, so I guess in the notes I'll just summarize this discussion with the ellipses there. But it is true that this theorem is known as Gauss's theorem. Okay, strange that my pen is not leaving the mark, a little trail behind it as it usually does. Oh, okay, now it's fixed. Good. Okay, good. So today is all about the divergence theorem, and so let's get to it. So I'd like to start the lecture with flux calculation, the sort of thing that will be made easier by the divergence theorem later. So here I wrote down a vector field, a 3D vector field. So this means for each point in space you get an arrow, something like this. Maybe my arrows are not really good, but I'm not really checking to see if the picture matches the formulas. It's just to indicate that we have a vector field. So we have a vector field and we have a box, right? We have here the set of all points in 3D space. So this is a 3D, a solid object where x is between 1 and 2, y is between 0 and 2, and z is between 2 and 4. And we want to know how much f flows, not so much through the box, I should have said out of the box. So I want to know how much f flows out of the box. I want to know the flux of f out of this box. So, and here it's important that I specify whether I am interested in inward flux or outward flux, because the two differ by a sign. So here we want to, so the flux, let me just summarize this by saying that the flux is the double integral over the boundary surface, the 6 sides of this box. It's the double integral over the 6 sides of f times n ds, right? So I should always remind you that n times ds is the same as ds with an arrow on top of it. Okay, good. So that's what the flux is. Here you see when I say flux, I need 3 things to compute flux. I need a surface, a vector field, and I need to specify the normal. Here I'm going to use, so my answer is going to be, so I'm going to use the outward normal in this example. So these are the normals I'll be using. You get one normal for each point on this surface, but the normal doesn't change in any single face. So I'm just giving you the normal at a single point along each face, on each face. Right, so so in green we see the normal vector fields, and I'm using the outward normal, so these are unit normals. The hat on top of the n indicates it's a unit vector. I'm using the outward as opposed to the inward because if I want that, if f points in the same direction as n, then the flux will be positive in the neighborhood of that point. So if I have a point where f points like this and n points like that, you see this is matching. This would be positive, and I want positive flux out of the box. So I want to use this normal. So let me just try to say that again. I want that if f is pointing like this, is pointing more with n rather than against it, then this dot product is contributing a positive amount to the outward flux. That's why I'm using this normal that points out. Okay. So we want to compute this. So in practice, this is going to be a little bit of work. We have 6 surfaces, and we have to compute an integral over six faces. There's really not much we can do except to compute 6 integrals. So this is going to be the integral over. Let me just call S1 is the front face. Let me just say S1 is the front face. Okay, so the one where this face over here, that's S1. So the integral here is really 6 integrals. The integral over S1 plus 5 other integrals. Right, these are manageable integrals, but still it's 6 calculations. So let's just understand. So let me just do this. Let me compute this integral with you, and then you'll see the process, and you see that if you wanted to, you can compute the integral over any of the other 5 faces, or all of the other 5 faces if you had to. And then you could compute the total flux. But let me just show you how to compute one of them. So here we're talking about the front face. Let's understand the front face. So what are we talking about? The front face has, X. So the front face is characterized by the fact that on this face, X, which increases this way, is the largest possible. So on the front face, X is 2. So let me just write this down. So on S1, which is the front face, X is 2. And okay, and then you get a square. So the front face lives in a copy of the YZ plane, but instead of having X equal to 0, on the front face X is equal to 2. And then Y and Z are constrained in these ranges. So Y goes from 0 to 2 and Z from 2 to 4. Let me write that down too. So Y goes from 0 to 2 and Z ranges between 2 and 4. Okay, now I want to describe points so I want to describe points, so I need to parameterize. Strictly speaking, to compute this integral over S1, you need to parameterize this face. But as it is a copy of the YZ plane, so for points here, I already know the X coordinate. If I can just describe them just using the Y and Z coordinates as the variables. So I'll use Y and Z as coordinates for these points with the understanding that X is always equal to 2 for them. So strictly speaking, using the language of parameterization, here we have R. So our parameters will be Y and Z, and the parameterization will be X is always equal to 2, Y is itself, and Z is itself. Okay, and the bounds for the 2 parameters are given here. Next up, if we're serious about computing this integral, we need to know ds. Right, we need to know n times dx dy. So, I'm sorry, n times the area element on the surface. And here I can show you. So the area element, my apologies, I kind of skipped ahead, got ahead of myself. So this face is just lives in a copy of the YZ plane. So area here is the same as area in the YZ plane. That's the dy dz. And the normal in green, so in green here, this normal over here, it just points in the I direction. It's 1, 0, 0. Right? I can see this from the picture. So this is 1, 0, 0 times dy dz. Right. The area element in this plane over here is the same as the area element in the YZ plane. That's dy dz, and then the normal is this. Good. Okay, so let me just do a parenthetical observation over here, namely that this. So I could have gotten this with the formula from last time. So last time I told you we were working with these cross products. So R sub, so we have the two partials of R, like this, right? And then if I did those two partials, so in this case, we're looking at the determinant. So this cross product is ij and k in the first row, then in the second row are the y partial of the parameterization, that's 0, 1, 0, and then the z partial of the parameterization, that's 0, 0, 1. If I work this out, I get I times 1, and then j times, so it's I times 1, and then j times 0, and k times 0 again. So here, this ends the parenthetical remark that you could get the normal, the unit normal. So last time I said ds with an arrow is the cross product times dy dz. This time I got the cross product from geometry. I knew what the normal was from geometry. And so I knew what ds was from geometry, and I knew what the normal was from geometry. So I was able to do it a bit quicker. But the two things are consistent. Okay, so let's compute and let's do the flux for the front face. That's the double integral. So flux through S1, that's the double integral over S1 of f. So what's our vector field? Y, z, x. Let me just write this. Let me write it all. So that's, now let me write everything in terms of the parameters. So the parameters are y and z. So y goes from 0 to 2. Z goes from 2 to 4. Right, they're from here, which came from this part. And then f, I just checked z, y, x. In terms of y and z, the parameters, I get z, y, and then 2, right, because x is 2. Because x is 2 on this plane, on this face. And then ds is just 1, 0, 0 times dy dz. Okay, so the cross product here just gives us a z, and then we're doing the integral of z, oops, here I put my differentials in the wrong order. So for this, here it's dz, dy, right? The inner, they should match like this. So because I set up the outer, the beginning of the integrals in that order, I was constrained to having the differentials in the opposite one. Okay, so here we're integrating z with respect to dz. I get z squared over 2. So we're just left with the integral from 0 to 2 of z squared over 2 between 2 and 4 dy. Now this thing here, I get 16 minus 4 over 2, that's 6. And then the integral of, and so this integral here is just 2 times 6, that's 12. Okay, I'll go back to actually this color, which looks a bit better. So conclusion, the flux through the front face is 12. And by going through a similar process, we could compute the flux through any of the other faces. But it turns out if we want to compute the flux of a vector field across a closed surface, we may be able to, we can compute it in a different way. Here's the thing, here's the statement, and I prepared the slide for you before the lecture. Here's the statement. So here's the situation. We're computing, so F is a vector field, any 3D vector field, and then we're doing the double integral of F around a closed surface, right? So it's not, so here, before I had the 6 faces, you know, of the cube, and that's fine, of the box, so that's fine. That's a closed surface. But if I had only 5 faces, that wouldn't be closed. If I had just, you know, the rectangle, it wouldn't be closed. It has to be a closed surface. It has to separate this a 3-dimensional space in 2 connected regions, the inside and the outside. And a closed surface does that. So we have a closed surface, and so the theorem says if we have a closed surface and we have a vector field, and here we're giving the closed surface the quote-unquote positive orientation. This means outward orientation. We call it positive because it's the one where the theorem works with the plus sign. If I had used the inward orientation, if these normals were pointing in, then the theorem would have a minus sign. So we have a vector field, a surface, and a closed surface. And the flux of any vector field through any closed surface, it's always equal with the positive orientation, with the outward orientation. It's always equal to something that's happening in the 3D region inside the surface. So here E is this solid region bounded by S. So the theorem says the flux is equal to the triple integral in this region inside S of the divergence of F. So the divergence, I recall, is a function, right? You build it out of the components of F. So let me just say we're integrating this function over the solid region inside E with respect to volume. And the function, the divergence is this function, right? If the first component of F is P, second is Q, and third is R, then the divergence is the first partial of the first component plus second partial of the second component plus third partial of the third component. It's really easy to remember. You can imagine as it being a dot product like this. So this is what the theorem says, and it's a pretty amazing result. I think it makes a lot of sense in physical terms. It has many interesting applications. So we'll see. So let me just mention one of these now. It's just a quick interpretation. Let's just interpret this in terms of fluids to see if it makes sense. So suppose that F is the velocity field of a fluid. Then on the left we have the flux of the fluid out of this closed surface. That's the amount of volume of fluid that leaves the surface per unit time. While on the right, we're doing a double integral in the region inside of the divergence. Now the divergence, remember, is this. If you take a little piece of fluid if you consider little volume inside E, and then pick a point in there and compute the divergence, that divergence is very close to the derivative of the, so this volume as time moves on, it moves to the side and it changes a little bit, and it may be increasing or decreasing. So if I start with a little volume here, it may be increasing, doubling volume every second or so, or it may be staying the same. But the point is, the divergence tells you the rate at which it's expanding. It's the derivative of the volume of an infinitesimal cube around the point. And so this is telling me how fast, so what's the amount of, this is the number. This tells me how fast volume is increasing inside this, the fluid is expanding inside the region, and if I add over the whole of the inside how much the fluid is expanding, the theorem is telling me that I get exactly the amount of fluid, the amount of volume of fluid that leaves the region. So it's right, and it kind of makes sense. Like whatever expansion happens inside E must cross the net amount of expansion or contraction that happens inside E. It has to be seen crossing this boundary somewhere. Okay. So this is the the interpretation of the divergence theorem in fluid mechanics. It has this theorem also has a bunch of uses in electromagnetism. It allows us to transform Maxwell's equations in differential form into global forms, into macroscopic. It allows you to go from microscopic to macroscopic things, to macroscopic descriptions that you can test. But I'll come back to this in a future lecture. Okay, So let's continue. Let's go back to our example. So here, let's use the divergence theorem to compute the flux of F over this out of this box, right? So we're going to need. So the ingredients are the flux through all 6 sides. So let's just say the flux through all 6 sides. I call that S. That's the double integral over all 6 sides. Here's something I didn't mention in the previous slide. So when we have a little circle around the surface integral, much just like with a line integral, the circle doesn't indicate a new kind of integral. It's just there to tell you that this integral is taking place over a closed surface. Right, so you can't, for example, take the upper hemisphere, that's not closed, but you can take the whole sphere, that is closed. So here, for example, it would be appropriate to put a circle because we're working with all 6 sides. So the flux through all 6 sides is the triple integral over the region inside, that's the whole box, of the divergence of F, okay, I can write it down. So div of F times dV. Okay, so let's on this side compute the divergence. So that's the x partial of the first component, that's z, plus the y partial of the second component, that's y, plus the z partial of the third component, which is x. So this is just, so that's 0 plus 1 plus 0, that's just 1. Constant, so this function is constant and equal to 1. And therefore, the flux is just 1 times the integral of dv, right? This 1 comes out. The triple integral of dv is just the volume of E. And the volume of E is pretty easy, right? It's just the product of the sides, the lengths of the sides. So in the x direction, the length is 1, and right from here, in the y direction, it's 2, and in the z direction, it's 2 as well. So as a result, I get 4. That's the flux through all 4 sides. Let me actually just do this here, because I would like to make a final remark here in the same slide. Okay, so now let's look at a quick bonus. So what about the flux through the remaining 5 sides? Here, let me just write words. So flux through other 5 sides, right? This is the double integral over the other 5 sides. Well, that's equal to the flux through all 6 sides. That's 4, minus the integral through the front side that we computed before, 12. So as a result, here I get minus 8. Okay, so what's our conclusion here? So our conclusion is, so let's suppose this F was the velocity field of a fluid. So if F was the velocity field of a fluid, then the divergence being 1 tells me that this fluid is not like water. It's actually expanding. It's not incompressible, but it's expanding as it moves around. So it's maybe like a gas, and the pressure is decreasing and the fluid is expanding, taking up more space. Okay, so we have there's a positive divergence. And if I look at this particular box, the amount of volume that crosses the box per unit time, the flux through all 6 sides, it's just 4 units of volume per unit of time. Okay, but interestingly, so the velocities are changing with position. And interestingly, for this particular box, through the front face, the flux through the front face is a positive number. Here I subtracted that positive number, but it's a positive number. It's 12. So 12 units of volume of this gas cross the front face per unit time. 4 across the all six sides overall on average. If the net amount of fluid leaving the region is 4 units per time. So this tells me that 8 units of fluid are entering the region through 8 units of volume of fluid are entering the box through the other 5 times per every unit of time, every second. So that's a pretty cool. Everything here is. This subject is very much alive. We can make sense of it. So finally, I would like to discuss show you the calculation at the heart of the theorem, at the heart of the divergence theorem. I want to show you a proof of a special case of the theorem, which shows you the calculation that allows you to one of these integrals. So let me just give you note that the divergence is often written as like this, as this dot product, and it seems like the integral is canceling. The innermost integral cancels with the derivative, and then you're just left with the double integral. It's more or less what happens in the proof. Let me show you how that happens. Okay, so here's a setup. Or we want to prove this theorem. Our goal is to show the theorem, the equation in the theorem, right? F here, our vector field. I wrote out the components, and the divergence, I decoded everything. It's everything in terms of components here. This is the divergence. So we want to check this. I'm actually going to check the theorem in a special case. I will assume there is no P, so P0, Q0, and then we're just left with this, right? And I'm gonna forget about this other slide for now. Just looking here, so it looks like a special case, but it's really the general case, because if I could check the same thing with for P00 and then Px, and similarly for 0, Q0, and then Qy, I would get 3 equations. If I added those 3 equations together, I would get the original equation back. Right. So this sort of thing is this simplification is not really making my life much easier, but it helps because it gives me fewer things to think about. All right, but now here's a kind of a serious simplification. I'll explain why it's okay to do this and how to go from this special case to the general case soon. But here's the assumption. I'm going to assume that. So we want to prove this equality, and here we have a triple integral. I'm going to assume that my region, it's easy to integrate over E in the order dz, dy, dx. Right, so if it's easy to integrate when E is inside, when dz is inside. It's one of those regions where you can have, so for each point in the region, you can integrate, so this region is bounded by the graphs of 2 functions. We have 2 functions of x and y, and E is everything in between the 2 graphs. And then for a region like that, we would work, and so we're looking at graphs over the same little domain D, and then to integrate over this region, we would dz would go up like this, right? For every point in the domain D of the functions, we would in this region D, the projection of E onto the xy plane. If I draw this vertical line, there is just a single segment. Okay, so that's the simplification. I'm assuming that my region is vertically simple. It's between 2 graphs, or equivalently, it satisfies the property that for every point in the projection of the region onto the xy plane, if I draw a vertical line through that point, then that vertical line meets E on a single interval. And then the endpoints of that interval just give you G and H. Okay. Also, I should let's just draw the normals here. So here we're using the normal could be changing, but it's going to be something like it's going to look something like this. Finally, there is the last normal here at the bottom. And I don't think it hurts to draw the vector field. So the vector field, maybe in blue, it's something like that. Oh, no. Actually, this vector field over here, the one I'm thinking about at the moment, has 0, 0, 0 for the first two components, so it's a vertical vector field. It's r times k, so it's really pointing up. So F is pointing up like this. Okay. So let's compute, let's do the calculation. So in this situation, let's just compute the right-hand side. So the right-hand side is the triple integral over E of the z partial of r. Right, so okay, so that's the thing we're doing. Let's set up this integral and see where we get. So this is, I'm going to set it up using a version of Fabini's theorem. I'm going to set up and saying for each, so we're doing a double integral over d. So that's with respect to dx and dy. And then for each point on this region, I'm integrating with respect to z on this segment over here. So z starts at being equal to h of xy, and it stops when it's equal to g of xy. Right, h is at the bottom, correct. And then we're integrating dr dz with respect to dz. Okay, so here this partial is a function of x, y, and z, but I'm just omitting the arguments. Okay, so here I didn't do anything yet. I just set up the integral. Well, I did use Fabini's theorem to set up the integral in that way, taking advantage of the shape of the region. But now we're not stuck yet. There's something we can do here. So here we're integrating. So when we're doing the innermost integral, we're fixing x and y, and then we're doing two things with x and y fixed. We're taking the derivative with respect to z, and we're integrating with respect to z. So these two things cancel by the fundamental theorem of calculus. So here I used Fabini, and now I'm going to use the fundamental theorem of calculus. So I get so the inside integral just becomes r evaluated at the top. So x and y are fixed, but z here is evaluated at the top. I get this minus r evaluated at the bottom. So x and y are fixed, but now z is equal to h of x and y. And then we integrate that with respect to dy and dx. So you see I got an integral. It's a little crammed. Okay, I'll just leave it like that. My integral now has two parts. Can I leave it like that? Maybe I can't. There's something inside me that doesn't let me leave it like that. Now we're integrating a difference of two functions. So so these two powerful theorems allowed us to go from the right-hand side, the integral of the divergence, to this double integral of a difference of functions. Okay, now let's compare to the left-hand side of the theorem. So the left-hand side here is the flux through. So the left-hand side is the double integral over the surface. So we can break this up, right? There is the double integral over the top, there's a double integral over the bottom, and there's a double integral over the sides, which go around as well. Right, there's the top, the bottom, and the sides. So let me just write that down. Double integral over the bottom plus the double integral over the sides. Okay, so let's work through this. So let's see if we set up the double integral at the top. Let's see what we get and compare it to what we already got. So the double integral over the top of our vector field, so this is 0, 0, r with times ds. So that's going to be what? Okay, so we need to we need to parameterize the top. So let's do it. So on the top, we're going to parameterize. So it's the top here is the graph of the function g. So can I say that we already know what ds is? We're going to parameterize the top by saying that x is x, y is y, and z is g. And then ds, so the parameters are x and y, and then ds, as we've seen before, is going to be minus the x partial of the function, so minus g sub x, minus the y partial of the function, and 1, multiplied by dx dy. Okay, I'm kind of feeling a little bit guilty for skipping this. So let me be brief about it. So r of x and y, so on the top it's a graph, so just say x is x, y is y, and z is g of x, y, the function. And then this thing here is, if we compute the partials, the two partials and take through a cross product, I get this thing. And the parameterization, so x and y here, this is important, I have to say they range in D. The points x and y have to be inside this region D. That's what this is the range for x and y. So now with this parameterization, I can set up the double integral at the top. Oh, there's one important piece of information here, so that I was missing. There is a plus or minus here. So here at the top, you can see that the normal is pointing generically up, right? If the z component of these vectors is positive, down here it's negative, but up here it's positive, the z component of these green vectors, of the normals. And so the direction of n of the normal is the same as the direction of ds. So I want the z component of ds to be positive as well. So that's why here we should take the plus sign. Okay, now let's set up the double integral. The double integral over the top, the surface integral over the top is just the double integral over d of 0. Well, can we just work out the dot product? So ds is here, and then we do this times that. I get 0 times this plus 0 times that plus r times 1. So I just left with r. Now r I have to express in terms of the parameters. Those are x and y. Okay, z, what's z in terms of x and y? That's given by this parameterization. That's g of x, y times dx dy, right? What remains of ds, which is the same as dy dx. So let's look at what we got. Let's compare what we had before. It's looking good, right? Before, so I said that the sum over all three sides was this integral over here, and now I said that on the other hand, so I want to show that this is equal to this. Okay, and now we just saw that, so this thing is the difference of two things. The first thing is the double integral over the top, right? This integral here, the integral of this is the double integral over the top. So it's looking good. So spoiler alert, this other part here with the minus sign is the double integral over the bottom. And the double integral over the sides will turn out to be 0. Let's just take a quick look why that's true. Well, the double integral over the bottom is exactly the same thing, but this time so the function is h instead of g, so that's one difference. And the other is that at the bottom, I want the normal to point down. The outward normal at the bottom points down. So I want to make this, the third component of n of ds, to be negative. So that's why I choose the minus sign. And the next thing is that, well, okay, so when I choose this minus sign, I get this minus sign over here. And so you see, it's exactly as I promised. The thing, the integral, here I get the integral of the function I'm subtracting over here. And finally, on the sides, well, okay, let's understand why this is 0. So this is going to be 0, but why? Well, so so the ds is n times the area element without the arrow, without the vector, and f is xxr, right? So this is f. Now, on the side, let's look at the picture. So on the side, f points up. F is vertical everywhere, in fact. But on the sides, of this region between two graphs, the normal is horizontal. So when I do the dot product f times n, I get 0 at every single point on the side of this shape. So the result is 0 because f is vertical while n is horizontal on the side of S. Okay, I said sides with a plural in the past, but I should have just said side. So from this picture, there's a single bound. It's like the boundary of this, but then there's a single side. It's a kind of a cylinder, slightly curved. So on the side, the normal is horizontal when it dotted do the dot product with this chosen vector field, which is vertical, I get 0. So this completes the proof in the case that I proposed that we study. So to close today's lecture, let me make a quick explanation, give you a quick explanation why this is all cases, why we've handled all cases of the result. So, I mean, why this discussion that we just had is really the heart of the theorem, So basically we want to piece together this result in a smart way, a bunch of these. Let me just make this picture. Let me just draw the picture. I think it'll be clear. So here's a picture that does not satisfy. Let's suppose we have a vertical vector field, right, like before. So f is going to be, just 0, 0, r. And we would like to prove the thing we had before, that the double integral over this torus, this surface of f times ds, we want to show that's equal to the triple integral over the region inside the surface, inside this donut, the solid donut, the integral of the divergence. Right, this is what we want. And here's how we get there. So we already know from the discussion we just had that if my region is vertically simple, I'm in good shape. So this region is not vertically simple, mind you. So if I look at the projection onto the xy plane, and I pick a point there and then draw a vertical line, I get, well, for some points I get a single line segment, which is good, but for other points, I get 2 line segments, so this region fails the vertical line test, right? And then I'm back to satisfying the vertical line test again. So here's how we can fix this. We can if I have a complicated region that's not vertically simple, that fails the vertical line test, I can break it into regions which are vertically simple. Right here, I could cut it along lines like this. Right? Then I would have, you know, this piece, and this you know, side, these two sides. So if I cut it with vertical lines like this, then I would know the theorem is true for each of these. For each of these three sides, like this piece, oh, four sides, I mean, this and this other piece. So that would tell me that the flux through the whole of this side, for example, so that includes the surface that we care about, but also includes these two disks here, which we really don't care about. So the flux through here. So I know this equation holds for all of these four things. If I add these equations together, on the right, I get the integral of the divergence on the whole region. I'm just breaking up the region and integrating one piece at a time, so that's fine. On the left, I get the integral over the original surface, plus a little bit of integral I didn't really care about, namely that these disks, I integrate over them twice. Right? Once, for example, this upper disk, I integrated over when I'm doing this part of the surface, but then I also integrate over it when I'm doing this piece over here. But notice that then I use I use opposing normals. Like here, I'm using the other normal at the second time round. And then the two fluxes, they cancel. They just differ by sign. When I add them, they cancel, and so the theorem is true in general. Okay, so this was a bit intense, but I think worthwhile. In any case, thanks for listening, and I'll see you guys next time.